In this lecture, we are going to learn about following topics: Introduction to gravitation, Newton's law of gravitation, projection of a satellite, and periodic time of a satellite. In today's lecture, we are going to know about what is gravitation. Now, what is gravitation? Gravitation is a phenomenon which leads two objects to get attracted to each other. So there can be any object which attract each other. We can take example of a bar magnet also, which attracts iron filings towards it. This is gravitation. Gravitational force between us and earth, this is gravitation. So this is called as gravitation. Next topic is Newton's law of gravitation. Now the law states that every particle of matter attracts every other particle of matter with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So let us see. Suppose these are the two bodies considered. They have their respective mass m1 and m2. Distance between them is r. Force exerted here between these two bodies, or gravitational force between them, is capital F. So we will write down the assumptions. According to the Newton's law, what it states that every particle of matter attracts every other particle with a force which is directly proportional to the product of their masses. Product means multiplication. So what are the masses? m1 and m2. Product of the masses means m1 into m2. So let us take it as equation number 1. Then it states that at the other half of the statement that the force is also inversely proportional to the what is the distance r. So square of the distance. Let us take it as equation number 2. So if f is directly proportional to m1 into m2 and if f is inversely proportional to 1 upon r square, then these both are equal as well. So we will write it down as f is directly proportional to m1 into m2 upon r square. But to remove this proportionality sign, we need to add some constant. So I am going to add a constant g, which is gravitational constant. So this proportionality sign gets removed and we get this. So this is our equation. G is known as gravitational constant. The value is 6.67 into 10 raised to minus 11 Newton meter square per kg square. So now what if we have to calculate dimension of gravitational constant? We just arrived a equation for Newton's law of gravitation, which is F is equals to capital G m1 m2 upon r square. We can remove g's value by keeping it at this side and shifting rest all on the other side. Okay, therefore g is equals to f, then this r square will come in the numerator, m1 m2. Okay, now if we have to calculate the dimension of g, what is the dimension of force? It is m1 l1 t raised to minus 2. For distance, it is measured in length, so L square. Since it is square, there are two masses, so m square. What we will do, together we will write it as, see, m1, then this 2 will shift upwards, 1 minus 2, L1 plus 2 t raised to minus 2 remains as it is. So our answer would be m, this is 1 minus 2 is minus 1, l 1 plus 2 is 3, and t raised to minus 6, which is the dimension of gravitational constant. Here we have to obtain relationship between gravitational constant and acceleration due to gravity when we are standing on earth. First, as we know that Newton's law of motion, we know that we just derive it as force is equals to capital G m1 m2 upon r square. But here we won't take m1 m2, so we will take it as capital G capital M small m upon r square. Capital M for mass of earth, this is r, capital R. Capital R for radius of earth, small m mass of the object or the body, g is acceleration due to gravity, capital G is gravitational constant. But when an object is on the earth, weight of the object is equal to gravitational force. Agreed? What is weight of the object measured in? mg. What is gravitational force here? Capital G m upon r square. This will be m and m gets cancelled. So this is the relationship, an expression or relation between acceleration due to gravity and gravity on the earth at certain height. So what happens here is, on earth, suppose a body is at a certain height from earth, h. So here is the body located. So what is the relation between acceleration due to gravity, which is g, and capital G at a certain height on this body? We know the relation of acceleration due to gravity, we just derive it, which is G is equals to capital G m upon r square, where assumptions are capital G is gravitational constant, capital M is mass of the earth, and r is the radius of the earth. Let this be equation number 1. Now for acceleration due to gravity at certain height would be gh. When this body is located at certain height on earth, so there will be two forces acting upon the object. First is the weight of the object and the gravitational force. Weight of the object is nothing but mg, since it is small body, so small m and g. Gravitational force is capital G m upon r square, but here it is located at certain height, so we will make slight changes. We will put an underscore h, and here G m remains as it is, but we will add some height here and square, because the height would be radius of the earth plus the height of the object. So we have substituted it here. After cancellation m and m, we get gh is equal to capital G m upon r plus h the whole square. Let this be equation number 2. Dividing 1 and 2, we get 2 by 1. So what is equation number 2? gh is equals to gm r plus h square. What is equation number 1? G is equals to, so we'll write left hand side and right hand side together. Gm gets cancelled. So what we get? Gh upon G is equals to r square plus r plus h the whole square. We can write this equation together. So it would be, we will take common square power for these. GH. So what we will do next step? GH is equal to, we will take G here, G R upon R plus H the whole square. So this is the gravity on the earth at certain height. This is a question, how two-stage launching system is carried on while launching a satellite. What happens here is, see, when a rocket is launched, the satellite is kept at the first part or the tip of the rocket. Now it is manually monitored, and after reaching a height, when the individuals or the people who are controlling this rocket think that this height is optimum or appropriate, so with the help of remote control, they detach the first part which has the satellite in it and rotate it with the help of the remote control in 90-degree angle. So here the satellite starts revolving around the earth. But here remember, students, that this height at which this detachment is carried on is very important to be calculated properly. Otherwise, the satellite can revolve around the earth in various other orbits. Know about it in the second part. What happens to the rest of the part of the rocket? It gets incorporated as space junk, and the main aim of the rocket was to launch the satellite, and so it starts revolving. Here there are various orbits of satellite which the satellite can go through. First, see, remember, VE is nothing but escape velocity. V is the velocity which is controlled by remote control, and VC is critical velocity. So first point is, when velocity of the projection is equal to the velocity to critical velocity. Critical velocity is the minimum horizontal velocity which is required for the satellite to move in a circular orbit around the earth is known as critical velocity. When this projection velocity is equal to critical velocity, the satellite starts moving in circular motion around the earth. But when the amount of critical velocity is less than the projected velocity and the projected velocity is less than escape velocity, so the satellite starts moving in ellipse format. This is ellipse. But when the projected velocity is equal to escape velocity, satellite starts moving in a parabola. When the projected velocity is greater than escape velocity, satellite starts moving in hyperbola. Here we are going to discuss about critical velocity of a satellite at a certain height and the critical velocity of the same satellite when it is very close to Earth. First we will take the case of when the satellite is at certain height. This is Earth. It will have some mass. Since the mass of Earth would be very large, so we are taking it as capital M. Radius of the Earth is capital R. At a certain height, when the satellite is at certain height, so height would be h, and it would have some mass, so small m. It would make an orbit, outer orbit. What would be our assumptions? Capital M is mass of Earth. Let us write down the assumptions. Small r is the radius of the outer orbit. So see, as you can see here, capital R, this is R, capital R plus h is equal to small r. So we will write it down, capital R plus h. VC is critical velocity, which is important. First point, see, for any circular motion of the satellite, the necessary centripetal force is, expression for centripetal force is FCP is equal to mv square upon r, equation number 1. since we are taking critical velocity, so we will write mvc square upon r. Second, there is some existing gravitational force between the satellite and earth, so which would be F is equals to g m upon r square. Since we are taking here gravitational force, so Fg, let us take it as equation number 2. But here gravitational force provides the centripetal force necessary for the circular motion of the satellite, so we will equate both the equation. Fcp is equals to Fg mm gets cancelled, 1 r from here gets cancelled. What is remaining? Vc square is equals to capital Gm upon r. We need the value of Vc, not Vc square, so we will take it as Vc and we will transfer this, and this will become under root of capital Gm upon r. Equation number 3. R, capital R plus H, so we will substitute it here. That becomes Vc is equals to under root of Gm upon capital R plus H. Equation number 4. Also, we derived earlier that at certain height acceleration due to gravity, what was it? Gh is equals to Gm upon R plus H square. We can remove its value, Gm value from here. What would be it? Gm is equals to Gh R plus H square. We can substitute it here. Vc is equals to Gh R plus H square upon R plus H. 1 R plus H gets cancelled, so our final Vc value would be under root of Gh R plus H square. This is critical velocity at certain height, so that is why we have acceleration due to gravity acting on a certain height, Gh. So just remember what you need in the answer. By that you can know how correct your answer is. So what would be the value of critical velocity at very close to Earth? First of all, our equation 4 would become Vc is equals to under root of Gm upon capital R. Since it is very close to Earth, so no need of height, so this would be our equation. And like this we can write Gm is equals to, since Gm is equals to G R square, correct? No need of writing H here. We will substitute it here. We will get under root of Gr square upon R. R and R gets cancelled. We know that Vc is equals to under root of Gr, which is nothing but critical velocity of a satellite orbiting very close to Earth. Let us know how much time period does a satellite take to complete one revolution. Again we have drawn a figure. See, this is Earth. Earth would have some mass, so capital M is mass of Earth, capital R is radius of the Earth. Satellite is at certain height, so height would be small h. The satellite would have some mass, so small m. Vc is critical velocity. As you can see how topics are interrelated to each other. So what would be the time period taken by the satellite to take a revolution? It would be time is equals to how much circumference of the orbit it is covering and with how much critical velocity it is covering the orbit. Circumference of the orbit, since Earth is oval or round, so circumference is nothing but 2 pi r. Critical velocity is Vc. So this is our expression. Let us take it as equation number 1. But we recently derived that Vc is equals to under root of capital Gm upon R. Let us take it as equation number 2. We can substitute equation 2 and 1. Substituting 2 in 1, we get T is equals to 2 pi r upon Gm upon r. T is equals to 2 pi r into under root of r upon Gm, reciprocal when we write these components in front of each other. Next step, T is equals to, can I take this r inside? When I remove it outside, it becomes 1 r. So it would be T is equals to 2 pi under root of r square. This r gets transferred inside into r upon Gm. R square and r, 2 plus 1, it would become r cube upon Gm. But here small r is nothing but capital R plus h. So we will substitute it r plus h the whole cube upon Gm. So this is our expression for time period taken by a satellite to cover one revolution around the earth. This is equation number 3. We can square equation number 3 on both the sides. We will get T square is equals to 4, 2 square is 4, pi square, r cube the whole square, so square root gets cancelled, r cube upon Gm. Here 4 pi square would be constant number and Gm also, so that means T square is directly proportional to r cube. That means square of the period of revolution of a satellite is directly proportional to the cube of the radius of its orbit. Here we have to derive an expression for time period of a satellite which is revolving very close to Earth. Again the diagram, capital M and R are mass and radius of the Earth, Vc is critical velocity, small m is the body which is revolving around the Earth. We just derived that time period of a satellite which is at certain height, so it has this height. What we will do, we are given the question where the satellite is very close to Earth, so no need of writing h. That means h is equals to 0. There is no height at end, so that means h is very equal to 0. This equation becomes T is equals to 2 pi r cube upon Gm. Correct? From this equation we can remove the value of Gm. So that means Gm is equals to gr square. Correct? Equation 1, equation 2. Substituting 2 in 1, we get T is equals to 2 pi under root of r cube upon gr square. R square and r square gets cancelled. T is equals to 2 pi under root of single r upon g. This is our expression for time period of a satellite which is revolving very close to Earth. Thank you for watching the video. If you like the video, don't forget to comment, like and subscribe. And if any doubt, you can email us at the given email address below. Bye.